Welcome. My name is Wang from Netflix, and today I'm going to talk about Netflix Kafka deployment in the cloud. I'm going to cover the challenges we have observed running Kafka, and then I will do a deep dive on the strategies and tools that we have developed to be able to run Kafka at scale. So first, brief introduction of myself. I'm currently with the real-time data infrastructure team at Netflix. I've been working with Kafka for almost 2 years. And I have been contributing to some open source projects, including Apache Kafka and Netflix open source software. Before joining the real-time data infrastructure team, I worked on the Netflix cloud platform team, where I built some key components in our infrastructure. Here are the highlights of our Kafka deployment in AWS. So on an average day, we have about 700 billion unique events injected into Kafka. And at peak, which usually happens around holiday seasons, we have over 1 trillion unique events every day. And at maximum, we have about 18 million events every second. We are managing over 3,000 brokers in 3 AWS regions. About 5 months ago, we have completed the migration of all our clusters from 0.8 to 0.9. And recently, we have also moved our Kafka clusters out of AWS Classic to AWS VPC, where we have enhanced networking. So today, I'm going to focus on the most important use cases we have in Netflix for Kafka, which is the Keystone Data Pipeline. So the Keystone Data Pipeline is a unified infrastructure for event publishing, collection, and routing for both batch and streaming processing. So Keystone Data Pipeline takes about 85% of our Kafka data volume in Netflix. So why Kafka? To answer that question, we have to go back a little bit into history. So our first pipeline is powered by Chukwa. And Chukwa is a log collection service originated from Yahoo. So we have event producers that send events to Chukwa, and Chukwa batch them and upload to S3. That's a very simple process. And around 2013, we decided to introduce Elasticsearch because we really like the search capability. Then there's a question, how do we send events from Chukwa to Elasticsearch? The sync to Elasticsearch is not as stable as S3, and we have observed a lot more latencies than the S3 sync. And we do need a large buffer between Chukwa collector and Elasticsearch to deal with latencies of Elasticsearch. So then we started to build file buffers by ourselves. And it turned out to be non-trivial. As soon as we realized that, we started to look around to find if there's any open source tool available, and we found Kafka. And once Kafka is introduced, we were immediately impressed by its performance and simplicity. And now, since data is already in Kafka, other teams start to ask us, can we consume at real time from the Kafka? Well, be our guests. And recently, we made another fundamental change to replace Chukwa collector with Kafka as the gateway for our data collection. And we hope this move will benefit all the data that are flowing in our system. So this is our current Keystone Data Pipeline architecture. On the left side, we have event producers, which send events to a set of clusters, which we call fronting Kafka clusters. And the event producers are essentially every applications in Netflix. And they send us the events by two approaches. For Java applications, they can send us the events using a Java client library that we provide. And for non-Java applications, they can send through the HTTP proxy. And once the events are in the fronting Kafka clusters, we use Samza routers to consume them and in turn send them to downstream sinks, including S3, Elasticsearch, and a different set of Kafka clusters, which we call consumer Kafka clusters, where the data will be consumed real-time by stream consumers. So one thing to note in this architecture is that we do not allow applications to consume directly from the fronting Kafka clusters. We want to ensure the stability and the availability of these clusters to producers. So what are the data that are flowing in our system? The first major category of the events are business-related. So Netflix is a data-driven company, and most of our decisions are based on data. So the business-related events include the user session information, which we use to track how users interact with our system. And that will include the results of a lot of A/B tests. And we also capture device logs. And these information are processed by our backend systems, and then feedback to the recommendation engines and algorithms that we use to control the streaming quality. And the second category of the events are related to system and infrastructure. These are typically application logs and request tracing information. And we use those information to gain insight into our infrastructure and use for debugging purposes. So now I would like to talk a little bit on how important the data is, because that's a fundamental step to further understanding our design principles. So if you ask your users how important your data is, and the answer will probably yes. And it's very important, and it's vital, and we use that for this and that. But if you ask them a further question, what can happen if you have some data loss? And the answers start to get interesting. So we ask these questions to our users, and the feedback we get is the business-related events are more important than the system and infrastructure-related events. So we should prioritize those. But even for business-related events, our data scientists told us that with a minor data loss of 0.1% or less, it will not have an impact to the data quality. And the other aspect is all of our Netflix applications have already adopted the approach of fallback when there's a failure. So for example, for the recommendation engine, if there is a temporary unavailability of the data or downstream systems, it will just fall back to display less customized information as opposed to fail miserably. So that means minor and short-term data loss will not be catastrophic. And finally, we are an entertainment company, and we serve paid customers. So the user experience is at the highest priority for us. That means we have to be able to let the user to start a streaming at any time, even if there's some difficulties in our system. And this leads to our design principles where we put the application's availability and user experience at the highest priority and is higher than our data. To achieve that, we use non-blocking event publishing. That means at certain times, some data might have to be dropped if they cannot be delivered over a period of time to ensure the availability of the applications. And at our data rate and the RPS of our services, even the slightest amount of time in blocking the application thread may lead to cascading effects to the downstream systems. And then that would naturally lead to the question, doesn't Kafka provide means for lossless data delivery? The answer is yes, in theory, but at our data volume, to be able to achieve lossless data delivery, the cost will be very high. So for example, we may end up to have a huge buffer at the producer side. And on the broker side, we may need to have at least 3 copies of data. And all these add up to cost. So now our strategy is to ensure a very high SLA, but not 100% for message delivery at a reasonable cost. Currently, our SLA is 4 nines, and we can usually achieve 5 nines or 6 nines. And the second goal for Keystone Data Pipeline is to keep the producers transparent to our Kafka deployment architecture or topology. So we used a dynamic mapping on the producer side to map the topic they want to publish events to the actual Kafka cluster. So this enables us to do things like moving topics around in different clusters and traffic diversions. And finally, to maximize our flexibility, we currently do not have keyed messages in our system. Because when we are delivering a non-keyed messages, we can choose any broker to deliver to. And here are the key configurations we have for producers and brokers. On the producer side, we have x equals 1. That means the leader of the partition does not have to wait for the followers to acknowledge the message. And that will improve the latency of the response to the produce request and minimize the chances that the producer buffer gets full. As I mentioned before, we use non-blocking for event publishing. And in case the buffer gets full, we just have to drop some messages. We use replication factor 2 for the brokers because using replication factor 2 will have adequate data redundancy, but at a very reasonable cost. We also allow unclean leader election for the brokers. That would maximize the availability of partitions to the producers. But for the consumers, if there's an unclean leader election, and if their consumer offsets get invalidated, they may get duplicate messages. So what are the challenges that we run Kafka in a public cloud? I think the biggest challenge is the Kafka is a stateful service, and we try to run it in the environment that favors static services. For example, the instances in the cloud have unpredictable life cycle, and they can be terminated at any time by the cloud vendors due to hardware failures or health check issues. And we have also seen plenty of transient network issues in AWS. Clients sometimes may have sudden connectivity issues to our brokers, and there might be a sudden surge of networking latency. I think for Kafka, it still has a long way to go to be more resilient to this type of soft failures. Outliers in brokers are a big problem for us. So the broker outliers are typically caused by bad hardware, noisy neighbors, or uneven workload. And we can typically tell the outliers by looking at its response time metric and TCP retransmits and timeout metric. The action that we take for the outliers is termination. So if a broker is an outlier, it typically will have a slow response to produce request. And that will result to the producer buffer getting full and the message drop from that point. But there's also a cascading effect of the outlier due to the interdependency of brokers. So let's say we have one broker that's replicating from the other 3 brokers. And this broker suddenly has some kind of networking problem, and it slows down the replication, and the replication lag will start to show. Once the replication lag has accumulated to a certain point, the data that it tries to fetch from the leaders become code, and it will be no longer in memory. So for the leaders, in order to serve the fetch request, it will have to read from disk. And when disk read happens, it will generally slow down the broker's performance to all kinds of requests, including the produce request. And then the producer will start to observe the effect of buffer getting full and message drop. And finally, zookeeper and controller-related issues often spell trouble for us. So there's one simple question. How many controllers can a Kafka cluster have? Is it 0, 1, or more than 1? So in theory, yeah, there should be only one controller for a Kafka cluster. But what can happen in practice? The answer to that is all of the above. So here I have a proof of the controller count become 0 for a Kafka cluster. So that you can see that this is a metric that we call active controller count. I'm showing the sum of active controller count of all brokers in the cluster. So it starts with 1 and it drops to 0 for about 40 minutes and then recover from that. So in 40 minutes of time, there are no controller for this Kafka cluster. What happened here? It turns out that in some edge cases, when zookeeper session timeout happens, the controller may get into an inconsistent state. So that's definitely some bad news. But the good news here is that these are not issues directly related to zookeeper itself. These are rather incorrect usage of zookeeper, especially in the controller code. And luckily, a lot of these issues are being identified as Apache JIRAs, and they are being evaluated, and hopefully they'll be addressed in the next major release. And the second issue that we observed from the zookeeper is that after a temporary zookeeper outage, it seems that the brokers is not able to recover from that, or the brokers is very slow to recover from that. So this is a true instance happened on the very next day when we turn on Keystone Data Pipeline powered by Kafka. So it starts with multiple zookeeper servers become unhealthy. And while we try to recover from that, we made a mistake when replacing the leader of the zookeeper cluster. And suddenly we lost the zookeeper quorum. And then you can see once that happens, the producer message drop rate shoot up to sky. So it reaches almost about 100%. So after about 15 minutes of struggle, we were able to recover the zookeeper cluster and the quorum. And we see a temporary recovery from the message drop from the producer side, but unfortunately, the drop resumed. And then we tried different ways to recover from that, including bouncing the controllers, rolling restarted brokers, but none of these helped. So this taught us a big lesson. So Kafka, as a stateful service, can be messed up really bad, and there might be no obvious way to turn it back. And in our regional deployment strategy, there are a lot of complexities. For example, we have clusters of more than 300 brokers, and even rolling restart those 300 brokers seem to take forever. And most importantly, if things like that happen in the future, we need to be able to recover quickly and restart fresh. So this leads to our current deployment strategy, where we prefer smaller and multiple clusters as opposed to one gigantic cluster. We now have between 20 to 100 brokers per cluster, and we believe that's the sweet spot for a Kafka cluster size. We also limit the number of partitions in the cluster to below 10,000. This is because that for a lot of Kafka operations, the latency of those operations are bound linearly to the number of partitions. So by reducing the number of partitions, we improve the latency and the overall availability of the cluster. And we also try to strive for even distribution of replicas for any given topic. So the brokers will get even workload, and we can eliminate the hotspot among the brokers. And instead of having one dedicated Zookeeper cluster, which we did before, we now have a dedicated Zookeeper cluster for each Kafka cluster. This will minimize the blast radius of the Zookeeper issues. So here are our deployment configurations for both fronting Kafka clusters and consumer Kafka clusters. So now let's get down to the cluster topology in AWS. So we have 3 auto-scale groups for each Kafka cluster and 1 auto-scale group per availability zone. So here, the availability zone in AWS can roughly be mapped to the concept of rack in data center. And we do not have clusters that across multiple AWS regions. But we do have use cases where we need to replicate data from a cluster in one region over the internet to a cluster in a different region. So let's say we have a cluster in US East 1 region, which I believe is right here in Virginia. And we want to send the data to EU West 1, which is located in Dublin. So we use Mirror Maker, and we deploy Mirror Maker in US East 1 region. And it will consume using the plain text because it's in the same region. It can just use the security group and the plain text to make things simple. Then, in order to send the data across internet securely, we use SSL for producing. The other alternative is to move the Mirror Maker to the same side as the destination cluster, which is in EU West 1. But then, the Mirror Maker will have to consume data securely over the internet. And once that happens, the consuming part will no longer be zero copy, which is a big performance hit for the brokers. So that's why we choose to put Mirror Maker at the same side as the source Kafka cluster. As I mentioned before, all of our Kafka clusters span across 3 AWS availability zones. And we use Rackware replica assignment, which distribute the replicas of the same partition to different AWS availability zones. This will ensure that in case of an AWS zone outage, the data will still be available. And this also helps us to improve the availability of the data in case multiple brokers of the same cluster are co-located on the same physical host in AWS. We contributed back this Rackware assignment to the Kafka community through the Kafka improvement proposal, and this is a part of the Kafka 0.10 release. So scaling is part of the important strategy for our Kafka deployment. The bottom line here is we over-provision our Kafka clusters for daily and failover traffic. So when I mention the failover traffic, it means sometimes we will divert a portion of the whole region's traffic to another. And we also have to scale up the Kafka clusters regularly for organic traffic growth. And we do capacity expansion in primarily two ways. One is to add partitions to the new brokers, and the other is to do partition reassignment. So adding partitions to new brokers is a fast way to expand capacity. You bring up your new broker, you add partition to it, and that's it. But the problem here is that the adding partitions cannot be applied to keyed messages. And when you have keyed messages and you're adding partitions to the brokers, there will be at least a short period of time where the message of the same key may be delivered out of order. And also, there's a caveat. The open source command line tool, which is called topic command for adding partitions, may add partition to existing brokers. So that sort of defeats the purpose because you are adding more load to existing brokers as opposed to the new brokers. So to mitigate that problem, we created our own tool to be able to specify the list of brokers where you want to add the partitions on. And we can guarantee that the new partitions will be only added to the new brokers.
Is that open source?
Not yet. And we occasionally do partition reassignment for capacity expansion. And the good news here is the partition reassignment can be applied to both keyed and non-keyed messages. However, the partition reassignment is a very slow process because the new brokers have to duplicate data from existing brokers, which are the current leaders of the partitions. And the new brokers cannot start serving the traffic until this kind of replication complete. And when this replication happens, there's a huge network traffic that may affect the producers and the consumers. So what we do here is we create our own tool to divide the partition reassignments into multiple small batches, and we only execute one batch at a time. This staggered way of doing partition reassignment helped us to limit the impact of replication traffic. And as I mentioned before, things can go really wrong for Kafka. So what do you do with a leaking pipeline? And our priority is to save the penguins. So the solution for that is built upon the elasticity of cloud, where you can quickly spin up a cluster and tear it down. And to be specific, we have a standby Kafka cluster for each fronting Kafka cluster. And these standby Kafka clusters are set up with minimal initial capacity to save cost. And they are ready to scale up at any moment. And for the standby Kafka clusters, we have a different Zookeeper cluster so that we can guarantee that there will be no bad state inherited from the original clusters. And we do even allow replication in the standby Kafka cluster because we want to get rid of any issues brought out by the replication. So this is what happens at failover. Assuming you have a pipeline working with producers sending events to fronting Kafka and send a router route the events to the consumer Kafka cluster. And all of a sudden, your fronting Kafka cluster is on fire. So what we do, we spin up the standby Kafka cluster, and we copy the topic metadata from original cluster to the new cluster. And in this step, there's no data copying involved. And we also need to spin up a new set of center routers that consume from the standby Kafka cluster. And the next step, we change the dynamic property on the event producer side to ask it to switch the traffic to the new standby Kafka cluster. So one thing to note here is, for the existing Samza router, we do not tear it down. So the data in the original Kafka cluster can be continuously drained, and we will not lose any data in this case. And the other nice thing about failover is that both the event producer and consumer are completely transparent from this operation. So these are complicated steps to do failover, and it's error-prone to do it manually. So this is why the automation comes to rescue. So with our management service, you can click a button to start this failover process. And behind the scene, management service will orchestrate through all these steps. And with that, we can fail over as fast as 5 minutes. Once failover is done, you have plenty of time to take out the metrics of the original cluster or look at the logs to find out where the problem is. Or you can completely tear down the original cluster and rebuild it from the ground up. So these provide an excellent opportunities for us to do offline maintenance, which you cannot normally get for Kafka. In fact, we leverage the failover process to do a lot of our maintenance, including the 0.9 migration and the VPC migration. So now let's pause here a little bit and look at the Keystone architecture once more to see what's the advantage of it. So on the producer side, because we have this dynamic mapping between topic and cluster, it provides the transparency for the producer and flexibility for the Kafka cluster, because we can move a topic around without even producer noticing it. And because we have this dynamic mapping, it enables the failover, which in turn greatly improves the data availability. And since the front-end Kafka cluster is only, So since the front-end Kafka cluster is only responsible for getting the events from the producers, and the consumer Kafka cluster is only responsible for delivering the events to the consumers, we can optimize each set of clusters differently to fulfill their purposes. And this isolation also improves our stability and controllability of the whole system. So now I'm going to introduce some of the tools that we have developed to enable us to run Kafka at scale. So the first thing is what we have for user interaction. So user interaction is an important aspect of our system. We want user to like our UI and the interactions. To start with, we have Google Spreadsheet for other teams to use when they want to create a topic. And now we have a nice UI, which we call self-serving tool, in our management service, where user can create the topics more conveniently. And while they are creating the topics, they can specify the set of routing rules that they want to associate with the topics so that these events will be automatically dispatched to different things. They can also specify some simple processing as part of the routing, for example, filtering or projection. And we spend a lot of time in monitoring Kafka. And we created our own dedicated monitoring service. So it helped us to achieve a lot of things. First, it registers itself as a Zookeeper listener, where it will get all the broker online and offline events from the Zookeeper. And secondly, it continuously sends heartbeat messages to all brokers and consume them. This is to ensure that the brokers are capable of getting the messages and delivering the messages. And most importantly, and perhaps interestingly, we use this monitoring service to monitor consumers as well. So to achieve that, the monitoring service first gets the rules from management service. It then gets the log offsets and consumer offsets from Kafka clusters. It will compare the log offsets and consumer offsets to determine the state of the consumer. For example, if it detects the movement of log offsets, but not the consumer offsets, it will declare that this consumer may be stuck. And if it cannot find any consumer offsets at all for certain topic partitions, it will declare that there are unconsumed data. And finally, the monitoring service publishes its findings as metrics to our backend metric systems, which we call Atlas. And Atlas will aggregate those metrics and then send the critical events to our alerting system. So Kafka metadata, which include the topic metadata, partition assignment, and ISR states, are critical information to gain insight into the Kafka brokers. But unfortunately, the UI for Zookeeper, which is typically exhibitor, does not provide a desirable view for the Kafka metadata. So this tree view makes it difficult for us to find a piece of information, and it involves a lot of mouse clicks in order to do that. Also, it provides no ways to correlate information. So we have created our own Keystone Dashboard where we have a much better view than the exhibitor. So here I'm showing the chart view of all the topics inside a cluster. And this is a table view of all the brokers in the cluster. So the columns of the table are all sortable, and the information in the table is searchable. And you can also conveniently find the controller of the cluster on the top. And in the final section, I would like to pay tribute to some of the key infrastructure components that we have in Netflix that help us to get here. So I have been working on infrastructure software for a long time. And building infrastructure software is like paving a road. Except for the initial excitement, for most of the travelers, they tend to forget the road. But in my opinion, if you learn to appreciate the road, and then your journey may become more enjoyable. So the first tool I want to mention is our Kafka deployment tool, which is Spinnaker. So Spinnaker is a general deployment tool, open source from Netflix. So we have closely collaborated with Google when we work on Spinnaker to ensure it can be used in both AWS and Google Cloud Compute. To me, the most enjoyable feature for Spinnaker is the deployment pipeline, where within minutes, you can create a complicated multi-stage pipeline that help you to automate your deployment process. So here I'm showing the actual pipeline that I use to move a Kafka cluster from the AWS Classic to VPC. And this is a 7-stage parameterized pipeline. And inside the pipeline, I have stages for baking the image, destroying clusters, deploying clusters, setting properties, and even invoking some Jenkins job. So this is super helpful, and it saves me tons of time. So when I use this pipeline to do the VPC migration, I was able to move up to 800 brokers in a day. And the second tool I want to mention is our configuration management tool, which we call Outliers, available from Netflix open source. So we use both Outliers to configure producers and the brokers. As I mentioned before, the dynamic mapping that maps the topic to a cluster is implemented on top of Archaeas. So the change of the value in the dynamic map can take effect immediately at runtime without having to restart the applications. And with the Archaeas, it aggregates all the properties available in your system and organizes them in a hierarchical way. So if a property exists in more than 2 layers, the one in the top layer will have precedence over the one in the lower layer. So this makes it very convenient for both applications and libraries to configure their properties. And you will always find an appropriate layer where you can conveniently override the value of the property. And that concludes my talk. If you want to know more about Kafka and Netflix Keystone Data Pipeline, you can go to our Netflix tech blogs, where you can get updated and more detailed information. So here, I'm happy to answer any questions. Go ahead.
One, Amazon has an offering called Kinesis that seems, as far as I can tell, to be hosted Kafka, or at least a very similar thing. What was the reasoning behind not using that?
When we start to build Kafka, Kinesis is a very early stage. And we are delivering more events than all the events combined in Kinesis. So that's reason number one. The reason number two is there's a very high cost associated with Kinesis. And we figure that if we use Kinesis, the cost for us for operating Keystone pipeline will be maybe 3 or 4 times higher.
You said that sorry, thank you, my second question. You said that the tools that you talked about weren't open source yet. Which ones are going to be open source, and do you know when? Like, is the whole Keystone pipeline going to be a Netflix OSS project at some point?
There's a general initiative to open source whatever available in Keystone pipeline, but unfortunately that's not on top of our chart as in terms of priority. So I think maybe within the next year you will see something available open source, but I cannot guarantee anything at this moment.
I also had 2 questions. So you said earlier that you had your failover clusters set up in their minimum configuration and that they can scale up dynamically from there. What do you use as the triggers to scale those up, and how does it handle what handles like what handles adding in new brokers to those failover clusters when they scale up?
If you are familiar with AWS, then basically that's a lot of functionality are implemented with the auto-scale group. So when disaster happens, as I mentioned, we have our automated tools where you can click a button and it will call a Spinnaker API, and the Spinnaker API will call the AWS API to scale up the cluster, to scale up the ASG. And the rest will be taken care of by AWS infrastructure.
And you said that when you deployed one autoscale group per availability zone, but that you do work across availability zones. Was there a reason that you do one ASG per availability zone instead of a single ASG that spans multiple?
So the reason that we have one ASG per zone is to provide the redundancy in case of zone failure. Does that answer your question?
So hey, you mentioned when you were showing the go live of Keystone was in October of 2015 date.
Yeah.
And you showed that there were some errors as a result of what looked to be Zookeeper. In November of 2015, Kafka 09 was released that, I don't know if it like fixed the Zookeeper problem, but it certainly made the interaction pattern with Zookeeper a little bit nicer. Can you comment on your experience with Kafka 09 forward?
I don't think any of the issues I mentioned here is fixed by Kafka 09. So in Kafka 09, the improvement regarding to Zookeeper interaction is the consumers do not need to rely on Zookeeper anymore. They talk directly to the brokers, but the brokers still have a dependency on Zookeeper. So from brokers' perspective, nothing's really changed. And the bugs that I've mentioned inside the controller are just discovered maybe a few months ago, and we reported to the open source community, and so they're working on it. I think in the 0.10 release, they may have to rewrite a large portion of their controller code where it interacts with the Zookeeper.
Thank you.
Hey, how are you? Really good talk, thank you. I have a less serious question, but is there going to be a Stranger Things season 2?
Yeah, of course.
Okay.
We'll keep innovating. Okay, thank you.